Thanks for the invitation, and also thanks, Stephen, for introducing the NNLIF model in the previous talk. I'm very happy to share our recent work here, and we propose a generalized solution for the NNLIF model. And this is a joint work with my supervisor, Xu'an Dou. So let me introduce the problem. To model a large number of spiking neurons, we can consider a mean field model in which the neural network is described by two quantities, a probability density P, which gives the wattage distribution, and the fan rate N, which gives the spiking activity. The meaning of the N of T is the number of spikes per unit time. And remarkably, as mentioned by Devin, the fan rate N of T can blow up. As in this figure, the fan rate N of T diverges to infinity in finite time. Mathematically, this means you cannot have a global classical solution because the classical solution stops when the fan rate blow up. And this is not just a mathematical issue because the blow up of the fan rate corresponds to the synchronization of a neural network, which in this context means the fraction of neurons spike at the very same time. So if we want to describe the synchronization in this mean field model, we need to answer this question: what happens after a blow up of the fan rate? And to answer this question, in this work, we propose a generalized solution from a new perspective and prove its global well-posedness. So precisely, we also consider the NNLIF model in which each neuron is described by its wattage or member potential. And the evolution of the wattage is subject to the leaky effect and a noisy external input. And when the wattage reaches a threshold VF, it's the neuron spikes, and the wattage is instantly reset at a lower value VR, and the spike will influence other neurons. Here is a typical trajectory of a wattage of a neuron. And in the mean field limit, we can derive the following nonlinear PDE for the probability density P and the fan rate N. In the advection term, the first term minus V denotes the leaky effect, and the second term describes how one spike influence other neurons. Just like in Devin's talk, if B is positive, we are in the excitatory regime, and the negative B represents the inhibitory regime. The diffusion coefficient also consists of two terms. If the first term A0 is positive, it denotes the external noise from the input. And the second term is the intrinsic noise, which is the noise due to the spiking activity we see in this neural network. And we have this parameter A1 non-negative. In analysis in many literature, this A1 is often said to be 0. When a neuron spike, when the neuron's wattage reaches VF, it spikes and it is instantly reset to VR. So we have a Dirichlet boundary condition at VF and the Dirac source term at VR. And the neurons reset at VR are exactly those who hits VF and the spike. So the coefficient here is the fan rate N of T. And the fan rate N of T is determined by the boundary flux at VF. Since the diffusion coefficient also depends on the N of T, so this equality actually gives a self-consistent equation for the fan rate. And for such a model, the fan rate can blow up in finite time. And mathematically, you cannot continue a classical solution beyond the blow up time. And indeed, as long as the fan rate does not blow up, it has been proved that the fan rate will remain finite. As long as the fan rate does not blow up, it is proved that you can continue the classical solution. So the blow up of the fan rate is exactly the obstacle which stops a classical solution. However, it does not mean the underlying physical process or the neural network also stop when the fan rate blow up. On the contrary, it means the blow up of the fan rate means the neural network synchronized, like 10% of the whole neural network spike at the very same time. This also relates to the multi-finite event, which is a recent concept in computational neuroscience. So to describe synchronization in the mean field model, we need to go beyond classical description and consider generalized solutions. And let me first give a brief review around the blowup for this nonlinear equation. And the nonlinearity comes from two parameters, the B and A1. For this, as long as B is positive or we are in the excitatory regime, the solution can blow up. And nevertheless, we can still have the existence of we can still have a global classical solution in the excitatory regime if we impose some conditions both on the parameter B and on the initial data. And on the other hand, if B is negative, we can also always have a global classical solution. However, most analysis literature for this equation focus on the case A1 is 0, including this existent result. Indeed, if A1 is positive, then no matter B is positive or negative, there always exists smooth initial data that leads to the blow up. And intuitively, we can write the fan rate as a function of the boundary derivative from its definition. And we can say to have a finite and non-negative fan rate, we need this constraint. And if A1 is positive, this constraint will imply a finite upper bound of the boundary derivative, which is difficult to satisfy. And for generalized solution, the pioneering work is this paper in 2015. They proposed a generalized solution based on the corresponding Minkine-Vilasov type SDE rather than this Fokker-Planck PDE. And in their definition, they make a clear link between the blow up of the fan rate and the synchronization of a neural network. They also prove the global existence of their generalized solution, yet they also only work with the case A1 is 0. And in this work, we propose a generalized solution from a new perspective. And in particular, our construction is only based on the PDE and work with the case A1 positive. So to summarize, with both mathematical motivation to have a global solution and the scientific motivation to describe the synchronization in the mean field model, in this work, we propose a generalized solution which allows the blow up of the fan rate and prove its global well-postedness. So the idea of our generalized solution is based on introducing a new time scale tau. We call it a dilated time scale. It is given by this change of variable formula, and it's related to the fan rate n. We can formally derive an equation in the new time scale tau, which I will show in details later. But the main points here are that the equation in tau, the blow up of the fan rate is allowed. And moreover, we can show that the equation in tau is globally well posed in the classical science. So now we have a classical solution in tau, and we want to define generalized solution in the original time scale t. To do so, we want to change back from the time scale tau to time scale t. And we want to find a change back map tau of t. And once this change back map is founded, we can define the generalized solution as time t to be the classical solution as time tau of t in the new time scale. However, this map is not trivial because tau of t can be discontinuous when the fan rates blow up. Tau of t can has a jump. And by the construction, the jump of of tau of t will lead to a jump in time of our generalized solution when the fan rays blow up. So when the fan rays blow up, the density function of our generalized solution will have a jump in time. And this jump in time is essentially contains how we resolve the blow up issue in our generalized solution. So let me explain more about this. We define the time scale tau where this change of variable from time scale t, but now we are in the time scale tau. We want to change back to t, so we invert this formula, and we want to define the map tau of t. But what we can directly define is the map t of tau by this integral, and tau of t shall be an inverse of this t of tau. However, t of tau may not be a strictly increasing function. Suppose in the dilated time scale tau, the fan rays blow up on the whole interval, then it means 1 over n plus 1 is always 0 on the interval tau 1, tau 2, which implies the function t of tau is flat on this interval, and all tau in that interval will be mapped to a single t star in the original time scale. So we choose tau of t to be the right continuous generalized inverse of t of tau, and it will have a jump at the blow up time t star. To summarize, in the time scale tau, the blow up of fan rays happens on an interval, but in time scale t, the fan rays just blow up at a single time point, and the whole interval is compressed to a single time point, which leads to the map tau of t has a jump at that point. And since our construction for generalized solution is to assign the solution in tau, solution as tau of t to be the generalized solution as t. So the jump in the scalar map tau of t will lead to a jump in the density function p. And we can say in the original time scale, when the fan rays blow up, the density function will have a jump in time as the blow up time t star. However, in the dilated time scale tau, the jump time t star is dilated to an interval tau 1, tau 2, and the jump as t star is dilated to a continuous dynamics in that interval. And let's watch the movie about this. So when the fan rays does not blow up, both the t time scale and the tau time scale are evolving. And when the fan rays blow up, the t clock stop, but the solution is still evolving in the tau time scale. And when the solution gets rid of the blow up regime, and the t time scale resumes to evolve. So we say the fan rays blow up in an interval in the tau time scale, and this is compressed to a point in the t time scale, and which leads to a jump in the density function before and after blow up in the t time scale. And let me explain more on the derivation for the equation in tau. So we recall the original equation in t. We do a reformulation in the reset term. We just substitute the definition of n of t into the reset term. And then we work with this reformulation. Since our generalized solution is defined by, since the time scale tau is defined by this change of variable, we just divide everything by n plus 1 in the new time scale. Just divide everything by n plus 1 for the equation in t. And then the time derivative in t will become the time derivative in tau. And we use the p tilde for the new density function in tau. And here, these coefficients are just divided by n+1. And we introduce the notation n tilde to write them. And here, the ellipsis just means this coefficient is the same as the diffusion coefficient. So we can derive the equation in tau. And here, the nonlinearity is in n tilde, which can be written as an explicit function of the boundary derivative. But here we just need to know that the blowup of the fan rate is equivalent to that n tilde is 0. However, n tilde becomes 0 is allowed in the equation in tau. Therefore, we say that the blowup of the fan rate will not hinder the evolution of the density function in the new time scale. Moreover, we can prove that the equation in tau is indeed globally well posed in the classical science. This is still a nonlinear equation because n tilde depends on the solution. However, this nonlinearity is always bounded. It's between 0 and 1 by its construction. So this is an advantage for global existence. And another point is, since n tilde is between 0 and 1, this diffusion coefficient is between A0 and A1, which are two positive numbers. So we have uniform parabolic, so the equation is uniformly parabolic. And here we rely crucially on that A1 is positive. In the proof, we adopt the framework for the classical solution for the equation in T in this paper. So we can have a global solution in tau, and by this change of variable, the lifespan of the solution in T is given by this infinite interval, and the global well posedness in the original time scale T is equivalent to that to show this T star is infinity. This is that's not necessarily true, and it relates to the long time behavior in tau. And our main analysis result is to study the global well posedness in T, and there is a crucial value VF minus VR for the connectivity parameter B. So if B is less than this value, we can always have global solutions. This including the case B is negative, and also the case B is positive but lower than VF minus VR. On the other hand, if B is greater than this crucial value, we can have initial data which leads to T star equals to 0. And by this definition, we can say T star is 0 is equivalent to that N is always infinity in the dilated time scale. And we call this case an internal blowup. So let me discuss briefly for the proof strategy of the global well posedness. We still use the notation n tilde. So this is indeed a long time behavior for the equation in tau. We first study a simpler case when n tilde is always 0. That is the internal blowup case. And then the equation in tau will simplify to this equation. I will label it as equation L. I will first give a detailed study for this equation. And then we can, for the general case, we can rewrite the equation in tau as the equation L with some terms involving n tilde. And suppose T star is not infinity, and we will get a smoothness of n tilde in the long term. So this infinite interval is finite. So this term will goes to 0 as time evolves. And then the long time behavior of equation in tau will dominated by the equation L. And then we can give a contradiction when the B is less than that crucial value. And to turn this intuition into rigorous proof, we adopt various estimates developed for the classical solution for the equation in T, like the entropy estimate and the super solution techniques. And to summarize, the blow up of the fan rate is mathematically stops the classical solution and is related to the synchronization. And in this work, we propose a generalized solution by considering this, introducing a new time scale. And in our generalized solution, the blow up, the density function has a jump when the fan rate blow up, but this jump will dilate it to a continuous dynamic in an interval in the new time scale. And to prove the global well-posedness in the original time scale, this is related to the long time behavior in the new time scale. And it's worth mentioning that there are two very recent preprints also use this idea of introducing a new time scale. As we study essentially different generalized solutions, and one difference comes from that we rewrite this direct source term. So there can be various generalized solutions, and therefore an interesting question is to consider physical criteria which can identify a physical solution when they are in a certain context, and another interesting question is to consider the long time behavior for the generalized solution. And welcome to read our paper on archive, and thanks for your attention.
Thank you so much, Xu'an, for your talk. I think we have time for one quick question, if anyone has a question. If you have, you can just unmute yourself.
Yeah, I have a question. I mean, how you get the idea of this new time scale which you introduced here?
Actually, we see this from a simpler model, which is we consider just an advection equation like partial t p plus n of t plus 1. The velocity is just n of t plus 1, and there's only an advection term. And we encounter this model in a different problem, and in that problem in that case it's very natural to divide everything by n plus 1, because there's only the advection term is like n plus 1 partial v, and which is very natural to divide everything by n plus 1, and then we think maybe we can use this on the NNLIF model. Let me find that paper. It's still during the we work on another problem, and there's a toy model which is nature to divide everything by n plus 1.
Okay. So you got idea from that model, and then you try to implement it in your model, and it works. Okay, thank you.
Thanks for the question.
Thank you. We have time for a super quick question.
I have another quick question. To have a fixed point for finding the n of t when you have a1 which is positive, can you have a case where you have multiple solutions, or can you avoid this? In principle, nothing prevents a case where you have multiple solutions for n of t when it's n equals something dependent on n. Yeah, yeah. This one, n of t equals minus a0 plus a1n. If a1 is positive, can you have a case where you have multiple solutions there, which will be another problem for distance?
No. We just interpret that if this constraint is satisfied, then n of t is given by this function, and if this constraint is valid, then n of t is infinity.
Okay. So it's, yeah, I wanted to be sure it's not an issue in the.
There is no multi-solution from this equation.
Okay, thank you.